Welcome back to ECE 442-542. It is nearing the end of the semester. Your final exam will not be this Friday, but the next Friday is our final exam. Just as a reminder, essentially 9 days we have our final. And you'll be finished with ECE 442/542 at 8 p.m. next Friday. Obviously I won't be, but you will be, is the idea. Homework 7 is due tomorrow evening. Homework 8, please stay tuned. I'm going to maybe make that extra credit somehow. I haven't decided what I will do with homework 8. If you are doing a project, that's due Saturday. Is that right? Saturday evening. Tomorrow's the 1st of May. Our final exam review is a week from today. It will be occurring immediately following our last lecture. That's what I'm planning, is to have a final exam review, unless you think that's not necessary. Let me know if you don't want the final exam review, and I won't hold one. That's fine with me. But we'll plan on a final exam review. Teacher course evaluations are due shortly after that final exam review. They are due before midnight on next Wednesday if you haven't completed your teacher course evaluations. I started writing things down. I was texting to myself in this list of goals, and I thought I better tell them some definitions. So when you see CTSS and DTSS, that simply means continuous time state space and discrete time state space. That's what I'm meaning by those abbreviations. Here is our list of goals, and we'll see how far we get. But some of this is actually a review for the final, in a sense. I'm giving you locations, time locations of lectures where this material can be found concerning, when we're doing full state feedback, we need a state space representation or a state space model. And we can get that many, many different ways. We could start with an inherently discrete state space, and then we don't have to create it. It's there, or we might have to find it. Somebody might give us a continuous time state space representation. We would then get the zero order hold equivalent, and we've done that already. Somebody might give you a transfer function in the S domain or the Z domain. If you're given the S domain, G of S, as the plant, then you would have to find one way to do that would be to get the zero order hold equivalent of G of S to get a G of Z. And in last lecture, we talked about going from G of Z through a block diagram to a state space representation. And you have this square dance of connections between these different representations. The time domain, continuous, discrete, frequency domain, continuous and discrete. Those four, and you should be able to sort of navigate your way around to arrive at a state space representation. Once you have a state space representation, we can then apply state feedback. And that simply means that we are linearly combining the state vector x, which if we have a state vector that's 10 tall, it might have some currents, voltages for its components. It might have position, velocity, temperature, pressure. All of those might be components in this state vector. Those then get measured, each of those, scaled by a scaling constant k. K is now a matrix, and it will weight each of those state vectors and inject that into the input of our system. And the idea is to create this gain matrix K to change the dynamics of our system. We may not be happy with the original dynamics of our system, and we want to change those dynamics with full state feedback. That's the idea. And we'll represent this in a general discrete time state space block diagram. By that I mean now we will have a block that's really a collection of blocks, but we'll just label it as a D, a delay block. But that might be, if we had a 10th order system, that's like a collection of 10 delay blocks. And we'll show how that is created in today's class. And we'll go through the process of designing this full state feedback gain matrix, capital K, which if it was a 10th order system and we had one input, K would be a row vector that's one high, it has one row, and it has 10 columns wide. That would be our K matrix. And we need to find the 10 entries in that K matrix. What are some issues? This will make more sense hopefully as we go, but we'll talk about these later. We need the full state vector available to perform full state feedback. That's something that we haven't been assuming. We've been assuming so far that we just measure the output and somehow filter that to adjust the system dynamics. Our system will need to be controllable, and we'll define what that means. And I might even give you another lecture offline for showing where that comes from. We're starting with the regulator design, and that will hopefully be explained later, and what it means to produce or introduce or incorporate a reference input signal into our system. All of those, I hope, will become clear as we work through today's class. Here's what we talked about last time. We have a state space representation, a DTSS, discrete time state space. Our system matrix is phi. So this is now our open loop system matrix. If our system is third order, phi is square, it's 3 by 3. Gamma is our input matrix. And that will typically be, we'll typically just be dealing with one input in this class, and for that reason the gamma will just be a tall, thin vector. It will be, let's say, 4 by 1 if we had a fourth order system. H, I'm using that instead of C because C a lot of times we've used for our controller transfer function, but H is now our output matrix. And if we need to, I've simply introduced some more variables. Little n is the dimension of our state vector. Little n could be 3, it could be 10, it could be 2, it could be 1. We could have a scalar phi. Phi could simply be a 1 by 1 matrix. U, we could have M, Michigan inputs, but typically M will be 1. And the Y, we might measure more than 1, but typically Q, again, might be just 1. We have a single input, single output system. Our assumption that we're living under, if we have full state feedback, is for the full state vector, all of those components to be available to be fed back. Here's the block diagram that I suggested we could create. And I've tried to indicate that that D block is a little bit particular or different than normal. And if you look at what little x of n plus 1, again, that's a vector, but if you look at the output of this summing junction and what makes that quantity, you can see that x of n plus 1 is phi x of n plus gamma u of n. And that was just our equation for the dynamics of our system. X of n plus 1 is phi x of n plus gamma u of n. We're now just writing that expression or equation in a block diagram form. We build up our output, or we create our output signal as a linear combination h times the state vector. And that's our output equation, y is equal to hx. Is that clear? And we can either write it this way, depending on how you like to think about things, or we could write it this way. And a lot of times I will not necessarily draw that sort of three-dimensional shadowing D to indicate that we have more delay blocks consistent with the size of our system, phi. If phi is representing a fourth order system, if this is a fourth order system, what's the dimension on phi? Phi is our system matrix, and it's always square, isn't it? So you can at least get a point or two by realizing that it's square, by saying it's 2 by 2 or 4 by 4. But if it's a fourth order system, phi is going to be a 4 by 4. If we had one input, gamma now is a 4-row, 1-column vector or matrix. And if we had one output, h is a row vector. It's 1 high and 4 wide. Let's return to what we had last time. Here is our example system. We started, because we've been playing the last few weeks with transfer functions, let's just start with, I thought, a g of z. And if you have that g of z, you should actually see the root locus for that g of z. Is it stable? Open loop. Is that system open loop stable? Why not? It has one of its poles outside the unit circle, and all it takes is one, isn't it? Can you stabilize this system with output feedback based on your knowledge of the root locus? I'm hearing some inconsistency. How about if I say it that way? We have a coin that we're flipping as a class, and some are saying yes and some are saying no. If I had flashcards, yes and no, what would your card be showing me? Can this system be stabilized with output feedback? Do you want to commit to an answer? How many think it can be stabilized? Well, do you feel comfortable showing a show of hands? Peer pressure? Yeah, you can always look. So I need the, and this is a classroom not designed for flashcards, because if now you can still look off your neighbor. But if you were all facing me, then if you just showed me your card, you couldn't see what were you answering? You couldn't sort of look off your neighbor. The root locus, this is screaming at us, so I'm just going to go ahead and draw this. I wasn't thinking this way until just now, but we now have that, right, in the z-plane. And if we don't have any zeros, we have two infinite zeros, and where are they located? At infinity. Right? Where are their angles? So you could have gotten some points if I said, where are the infinite zeros? And you say, oh, at infinity. Well, I have to give you some credit for that. They are at infinity, but now where's the fundamental angle? 90 degrees, because it's 180 divided by 2. So now this actually, because it's two poles, it's going to split right equidistant between those. One's going to go up, and that's all supposed to be on the real axis. I for some reason couldn't sketch it properly. And one's going to go up, one's going to go down, plus and minus 90. They're intersecting right at 1. So the best you can do is for it to be marginally stable, and I wouldn't like that at all. I wouldn't want to be right at 2 poles at z equal 1. That's a bad system to be trying to live with. You just bump it with a constant and it's going to go crazy. It's actually unstable if I have 2 poles right there at the z equal 1. Can't even hope that this be marginal. Okay? Because now if you have any kind of an initial condition, it's going to go unbounded. What we want to do is design a full state feedback control. No longer a C of z. We want to design a full state feedback control. And we derived this state space representation last time. It's not necessarily a unique. You could come up with a different state space representation to lead to that same transfer function. And if you did, your feedback gain matrix K will be different from mine. But hopefully we would put them at the same locations if somebody said, locate your closed loop poles at a certain spot. Here is the equation for full state feedback. U is minus K x of n, some linear combination of our state vector. And in our example, we had one input, we had 2 states. K is now a row vector with 2 independent variables, K1 and K2. This is no longer output feedback. This is full state feedback. That's why that root locus now is going away with full state feedback. But I just wanted to think about what would happen if we applied full output feedback around that. And what we want to do is we want to select K to change the system dynamics. And in particular, where would we want those poles, which are the eigenvalues of our closed loop system matrix, which I haven't yet derived. We want those closed loop eigenvalues, which would be the poles of our closed loop system. Where do we want those to live? And that's not a hard question, I hope, at this point in the semester. Where do we want our closed loop poles? Inside the unit circle. So we want the eigenvalues of our closed loop system to be inside the unit circle. Here is a more specific block diagram of what we're trying to accomplish. This shows you in a block diagram what full state means in this 2x2 or this second order case. The green should be the block diagram that we derived last time. And we labeled the states to be the outputs of the delay blocks. And here I'm simply saying, let me call that rightmost delay block x sub 1, and the next delay block will label its output as x sub 2. Those are now my 2 state variables. And if you write x sub 1 of n plus 1, you better get the first row of that state space representation. And if you write an equation for x sub 2 at time n plus 1, you better just get 3u of n before we add in the full state feedback. And the full state feedback simply means that you are accessing every one of the state variable components, x1, x2, if it was 4th order, x3, x4, feeding those back with an independent gain value. And this now interconnected system allows us to change the dynamic behavior. Is that clear? Here's what we want to do. So now we have from that block diagram, or from any, we actually have x of n plus 1 equaling phi x of n plus gamma u of n. Phi is our system matrix, gamma is our input matrix. We want to control that system with a full state feedback. And K now is a matrix. This is, I guess I haven't necessarily labeled that. This is our state feedback gain matrix. That's just a matrix of constants that we are going to find or try to create. If we now apply that particular structure for the input, u, into our dynamic equation for our system, we will now close the loop. We will obtain a closed loop. This was our open loop system matrix. And this is our input matrix. Let's now combine that u, particular structure, with the dynamics. We now have x of n plus 1 is equal to phi x of n plus gamma, but now u is going to be replaced with a minus k x of n. Meaning k, this matrix, has to be compatibly dimensioned with all these other matrices. By that I mean the matrix products and the matrix sums need to be consistent. Meaning gamma and k better be compatible for a matrix product. And if gamma is one column wide, that's why k needs to be one row tall. But their product now expands to a square matrix. Gamma k is now dimensionally the same as your phi matrix. In this example that we've been talking about, we're talking about 2 by 2 matrices. But if we now combine the x vector or factor that out of these common terms, we can now say that phi minus gamma k is going to be the matrix that scales the state vector, x of n. This is now x of n plus 1, and I might call this a new matrix, phi sub c, and instead of being the open loop, we've now modified the open loop dynamics to be closed loop. This is what I would say phi is now the closed loop system matrix. For our example, we can now say that phi sub c is equal to this phi minus gamma k, but phi was just 2, 1, 0, 0, if I remember right. Our gamma had only one non-zero entry, and it was in the bottom row. The top row was nothing. And now our K matrix, I can't draw or write K's, so you'll have to improve your penmanship. That's, ooh, that looks awful. That's a K sub 1. I don't know what happened, but don't tell my writing teacher. K sub 1 and K sub 2. And that's our full state feedback gain matrix, capital K. But you can now see, I hope, where these K's are going to come into play in this 2 by 2 matrix. None of them are going to be adjusting the top row because they're being scaled by 0. The bottom entries will be scaled by 3, and you'll now have independent control over the 2, 1 entry and the 2, 2 entry in that closed loop system matrix. Phi sub c now, if you do the multiplication and cleaning up, phi sub c now becomes 2, 1 upstairs, but downstairs it's minus 3k1 and minus 3k sub 2. Is that okay? Everybody clear with where that comes from? And now what we're interested in is we're actually interested in the eigenvalues of this closed loop matrix. We want to adjust or select K1 and K2 to give us eigenvalues which correspond to the closed loop poles of our system. We want to pick K1 and K2 to put us where we want those poles to live. If we now look at the eigenvalues of the closed loop system matrix, suppose that I now call those, just because I'm going to have variables, k's in there, I'm going to call it delta sub k of z. That's now this determinant of zi minus phi sub c. That's how I find the eigenvalues of a matrix. And phi sub c on the final might be a 10 by 10. So now you have to compute the determinant symbolically of a 10 by 10 matrix. So you might want to learn that before next Friday. Your calculators actually will do that, but it may take them a while. So this calculator needs to be able to do it. If you're listening at home, I'm pointing to my head. Your upstairs calculator needs to be able to compute this for a 2 by 2. That shouldn't be a stretch. But if we do that now, for this example, I'm going to do it in the long way. I have z, which is a scalar, times I minus phi sub c, and phi sub c I still have up there. And these vertical lines are indicating determinant. And what's in this yet to be written matrix? That's my I, isn't it? It's an identity matrix, and it has to be the same dimension as phi. And the identity matrix is just ones on the diagonal, and the square matrix is compatible with the phi sub c. And now the z's become elements on the diagonal, so that I now have z minus 2. I have 3k sub 1. I have minus 1 upstairs, and I have z plus 3k sub 2 downstairs. And if I compute the determinant of that, I have the product of the diagonal pieces, or elements, for a 2 by 2, minus the product of the off diagonals, and that minus 1 will change the sign of the minus to where I now have a plus 3k sub 1. So make sure I'm not falling asleep on this computation. And if I put all of these pieces together, if I form that, I now end up with something that I would expect. I had a second order system. I better end up with a second order denominator. I have a z squared. Then I have, how do I want to write this? Let me say plus a minus 2 plus a 3k sub 2 z. Is that right? Minus, or a 6k sub 2 plus a 3k sub 1. And what you're looking for, hopefully, is the ability to independently adjust every coefficient. Well, since this is monic, does everybody know what monic means? For a monic polynomial, that just means that the highest power coefficient has been normalized to 1. And typically this will end up with being a monic polynomial. You've normalized your polynomial to where the leading coefficient of your highest power is 1. What you want is the remaining coefficients to be individually or independently adjustable. And you can see that that's true in this case. The linear coefficient we can set to whatever value we want by the choice of k sub 2. And once we've picked k sub 2, that's fixed, but now this constant coefficient can be adjusted by adjusting k1 to be whatever value we need it to be. That's what we're wanting to do. So here's the process then, and we'll work through it for this particular example. But this generalizes, this process of designing K generalizes to any order system. It could be a 10th order. What you're doing then is this design is really a process for finding that matrix K, which is our full state feedback gain matrix. And in our example, K just consists of two unknown coefficients, K1 and K2. This process now for designing K has, I'm going to break it into 3 steps. The first step is you need to decide on desired closed loop pole locations. For our example, how many poles do we need? And now this is why we've been harping on where do we locate our poles? Because now you better have a little bit better feel for where those poles are located. You know these hearts in the z-plane. You know these concentric circles. You know these angles. You know how all of those play together to give you desired regions in the complex z-plane that you might want your dominant poles to live. If you know something about the percent overshoot requirement, something about the settling time, something about the peak time, all of those influence where you are inside the unit circle. Is that clear? That's step 1, is where do we put, and if you had a 10th order system, you might pick 2 to dominate your behavior. Do you know what that means? Those are the slowest of your closed loop poles, and then you pick the other 8 to be inside those by some factor so that they don't really mess up that dominant dynamic behavior. So you might pick a couple at 0.9 plus and minus j 0.1, and then you might put the other ones at 0.8, all 8 of them, just to simplify your design. That's one example. Here we only have to pick 2 because we have a second order system. In this case, let's just suppose that we want our z delta to be, obviously I have something for that location, but there really isn't anything special for that location, but 0.8 plus and minus j 0.2. But you could now sketch that and figure out what that corresponds to in terms of a pure 2-pole system behavior, if you wanted to. That's the first step, is picking that set of closed loop poles that you want to end up with. The second step is to create the polynomial that possesses those as its roots. So create the desired, let me call it the characteristic polynomial. Using all of these coefficients or locations in z sub d, and let's call that delta sub d of z as some polynomial. So that delta sub d of z in this example is going to be z minus 0.8 minus j 0.2. That's the z delta in the first quadrant. And then we have z minus 0.8 plus j 0.2. That's the one right below it in the fourth quadrant. Or what value of z causes this first factor to vanish? and what value of z causes that second factor to vanish. That will give you those pole locations. And now we can multiply these out, but it's easiest if you sort of collect these pieces in this way. And now just take the red pieces and multiply those with the imaginary pieces. And I hope you see that the cross product terms cancel because of this complex conjugate pole pair. But we still end up with z minus 0.8 squared, and we have a minus a j squared, which gives us a plus 0.2 squared. So when you write down z delta of 0.8 plus or minus j.2, you could have immediately written down this structure for your characteristic polynomial. And now if we multiply that out, we have a z squared minus 2 times 0.8z plus 0.8 squared plus 0.2 squared, or this is now z squared minus 1.6z plus 0.64 plus 0.04, or 0.68. And that is now our delta sub d of z. That's our second step in this process. The third step is to equate the two polynomials. We had our delta sub k polynomial and we have our delta sub d. We need to make sure that those are equal by the choice of our unknown k's. So that's step 3, is equate the coefficients in the two polynomials. In this example, to find k, which is actually k1, k2. Meaning, we had a delta sub k of z, which was z squared. Well, how do I want to do this? Sorry. What did I call the last one? Was it delta sub d? Okay, desired. That's what we're wanting to do. The delta sub k of z equals the delta sub d of z. And from what we had z squared plus minus 2 plus 3 k sub 2 z plus 3 k sub 1 minus 6 k sub 2. I hope that's what we had for delta sub k of z from before. And we need that to equal z squared minus 1.6z plus 0.68. Or now we simply need to equate the coefficients in the two polynomials. If we look at the linear coefficient, or the coefficients for the z to the first power, we have minus 2 plus 3k sub 2 equaling minus 1.6, or 3k sub 2 ends up being 0.4, or k sub 2 is a third of that. We found k sub 2. And in general, these equations may end up being coupled. If you now had a 10th order polynomial, it may end up that you have 10 coupled linear equations that you have to now solve for those 10 unknown k's. In this particular case, the k2 and the k1 did not both appear in the z1 coefficient, and so we could immediately solve for k sub 2. Is that clear? It could be, depending on how the coefficients end up resulting with your determinant, you might have a k1 in that z coefficient. And if that's the case, then you're going to have two equations and two unknowns to solve for. Here we sort of lucked out. K sub 2 then is this 0.133, and if we now look at the constant coefficient, we have 3k1 minus 6k sub 2 equaling 0.68, and k sub 2 we've just determined to be 0.4 over 3. And now we have that 3k1 is equal to 0.68 plus 0.8 over 3. Is that right? No. Wake me up. I got rid of that 0.3, didn't I? I canceled it. Or I got rid of the 0.3, so I just have somewhere, if I can find my eraser, is just 0.8. So that now K1 is 1/3 of that sum. Or 1/3 of 1.5, essentially, almost, and that's roughly a half. Or if you do the multiplication, it's 0.4933. We've now found our K. K is now K1, which is 0.4933, and K2, which is 0.133. That's what we were looking for, and we can now compute our full state feedback system matrix phi as this linear combination. And if you do that, we are not touching the top row, but in the bottom we end up with minus 1.48, and we have minus 0.3999. Obviously I have some rounding here, but that's close enough. And if I compute the eigenvalues of phi sub c, those end up being where I thought they should be, 0.8 plus and minus j 0.2. Questions on that? And that's how you could do this by hand. If you had MATLAB available, which you won't have during the exam, you could use MATLAB. Let's say to check your work on homework number 8, if I ever assign homework 8. Meaning, here is our phi matrix, which was what? 2, 1, and then nothing in the bottom row. That was our system matrix. Our input matrix was 0, semicolon 3. And we wanted our closed loop poles, let's say desired poles, to be at 0.8 plus j times 0.2, semicolon 0.8 minus j times 0.2. And somebody at MATLAB has obviously wanted to solve this problem before, so they have a function to do this for us. There's many functions, but one of them, which is sort of easy to remember, is to say place. say place, and now give it, oh, it's telling me what to give it, A, B, and P. But my A is the open loop system matrix, which is phi. My input matrix was gam, short for gamma, and my P is the desired pole location. And now I get my full state feedback gain matrix K with about 3 clicks in MATLAB. Is that okay? A way to check your answer. What's the answer in the back of the book? We don't have a textbook for this class, but you now have MATLAB, right, that you can use. So that's quickly showing how to use MATLAB. Is it always possible to do this? To move, and well, I'm getting ahead of myself. I'm wanting to keep jumping around. When is it possible for full state feedback to position the closed loop poles arbitrarily? And obviously we want to arbitrarily place them in a desired region in the unit circle. And now I just remembered something else. So I'm going to jump back. We could now compute or check our answer within MATLAB. We could say, oh, I don't know if this was the right command. We could say phi closed loop, that's the closed loop system matrix, is now phi minus gam times k. There's our closed loop system matrix, and that should be what we calculated. And then we could say, oh, what are the eigenvalues of our desired phi matrix? That's just EIG phi closed loop. And those are where we thought that's where we wanted them to be. 0.8 plus and minus j 0.2. And I'm assuming you have young eyes that you can see that font. And if you can't, I guess you can watch this video. It's occurring about 30 minutes in. So you don't have to watch 45 minutes in. I'll have to reset my timer. Well, I just gave myself 15 more minutes. Ooh, getting some stares now. All right, so back to the notes. When can we do this? When can we arbitrarily position closed loop poles with full state feedback? Did everyone read the textbook ahead of class? And I just commented that we don't have a textbook, so I'll just tell you when this is possible. This is possible, and now when you go home tonight, you can tell your friends and neighbors and roommates when you can control arbitrarily the poles in your closed loop system matrix with full state feedback. You can say the system has to be controllable. When the system is controllable. So let me give you, I'm almost tempted, since I just lost 15 minutes, I'm almost tempted to just kind of give you what controllable means, and then we'll go on. And I'll save the details for some other time. What does it mean for a system to be controllable? Let me do it another way. A system is controllable if and only if, now we're getting sort of theorem-y, but this is now a script C for the controllability matrix. I'm now going to build that up with a collection of columns. Gamma, remember, is my input matrix, and it could be m columns wide, but in this class probably it'll just be one column wide. It's n rows tall, and now we take that and we hit it on the left with our system matrix, phi. And these are the open loop matrices. Then we just keep hitting it with phi, higher powers of phi. And we keep doing that until we get tired, and when we get tired is when we've multiplied it up by the power n minus 1, where n is the dimension of our phi matrix. For a second order system, this isn't too hard. Oh, a system is controllable if and only if this controllability matrix C is full rank. Everybody had linear algebra. You know what full rank means? This now has to have rank little n. It might have, if gamma has more than one column, this controllability matrix might be really wide, but it's always n tall. And we need n of those rows to be linearly independent. We need all n rows. In this class, if we let m, the number of inputs, equal 1, then we can just compute the determinant, and we want the determinant of C to be non-zero. If m is equal to 1, then we could say the determinant of C needs to be non-zero. That's how we could check for controllability. In our example, what did we have? In our example, phi was 2100. Gamma was 0.3. So if we computed this controllability matrix, we have a 0.3, and then what? Well, maybe I'll do it this way. Why don't I say this is now gamma, phi gamma. How many more of these do I have to push on the right? That's it, isn't it? Little n was 2. I need to keep going until the power of phi is n minus 1. Or in this case, 2 minus 1, or I have phi to the 1 power. This now says that my controllability matrix is 0.3, and phi times gamma. That gamma is just pulling off the second column of phi, and it's scaling it by 3. So this now becomes 30. And I hope you can see that the rows of C are linearly independent, or the columns of C are linearly independent. Or if you can't see that and you compute the determinant of C, it's going to give you something not equal to 0. What is the determinant of C? If you did that, you said, well, I don't think he's going to believe me when I say I know that that's full rank, so I'm going to just compute the determinant. It's the product of the diagonals, which is 0, minus the product of the off diagonals, and that's not equal to 0, is it? Minus 9. So it's full rank. We have a completely controllable system, and so that particular system, even though it started with open loop poles at the origin and at 2, which was unstable, we could put those anywhere we wanted inside the z-plane, and we would probably prefer to have them inside the unit circle in desired regions. Questions on that? Does everybody know how to do that? That's problem 1 on homework 8, is this process, full state feedback. That's what I'm thinking. Who knows if what will happen. Let's move on then. It looks let me ask you a question. Are we getting away with something? Because what now, wait, why did we spend all semester playing around with this root locus, trying to design controllers? It was kind of hard. It was kind of, where's the root locus? How do we bend that inside the unit circle? And now you show me this, and I can do them, put these anywhere in the unit circle. What's going on? What's different now versus last lecture? What are we assuming with full state feedback? Or are we getting away with something? Or what's the difference between today and last lecture? Full state feedback is in the description, right? Full state feedback. Up to this point, we were using output feedback. Output feedback, only output, not some linear combination of every one of the possible state variables. We were just using some linear combination of the state variables as the output and feeding that back. So we're doing something quite different. Full state feedback requires access to each component of the state vector. So if you compared this with constant output feedback, this is constant full state feedback, but now if you have a second order system, you have two linearly independent variables that you can adjust, whereas in constant output feedback, you just had one, and the closed loop poles always lived on the root locus. Now, if your system is completely controllable, you can put them anywhere you want in the unit circle by the appropriate choice of these gains. But we're requiring now, if you had a fourth order system, let's say this modeled some engine, and maybe one of the variables was the internal temperature of your motor. Now you're assuming you have access to that variable. Maybe you don't have a sensor that is available to make that measurement. Maybe you can't measure the velocity of some quantity. Maybe you can't measure a current that is in your model, and that's one of your state variables, but you can't measure it. Then you can't have full state feedback. We'll get around that next week. I don't think I'm going to get there, but we will build full order estimators, which will allow us to estimate every one of these silly state vectors components if we don't have them available for measurement directly. But we're not there yet. Let's now look at if there are other concerns besides just what we've said. Are there any other concerns? And a lot of times when I'm looking at something, I like to draw a picture. I know my drawing is pretty poor, but it still kind of helps me think. What do we have? Well, we have a state space representation, which has an input matrix. There's our gamma. That's going into a summing junction, and then that's going into this three-dimensional block of delay elements, D, to produce the state vector at time n. So this location, that signal coming out of that summing junction is x of n plus 1. Here is u of n. We measure this, or we have in our model, in our system, we have x of n plus 1 created by a linear combination of the states interconnected with the system matrix phi to make phi x plus gamma u, and that now gets all those state vectors are combined to produce our output y of n. And this, is our system. I could maybe wiggle the input and measure the output y, and what's happening inside is my model. But I've now modeled it in the state space representation, or using a state space representation. And that's what that looks like there. But now what am I doing? With full state feedback, I'm assuming that I can go in and I can measure that x. So that's the same signal. I can just pull it off here. I scale it by k. And it's easier, actually, if I go ahead and put my minus sign there, and then I don't have to indicate a sign on my summing junction. But this is now what I'm doing with full state feedback, isn't it? I'm simply measuring the full state vector x, scaling it by k, this matrix k, and using that to create my input u into the system. Does this picture provide you any more insight into us getting away with something? So let's look at the picture a little bit more. And remember, we could say, if I ask you what's possible with this configuration, you would say, well, if the system is controllable, then we can find a matrix K that will locate the closed loop poles anywhere we want in the z-plane. Or K can adjust the system dynamics arbitrarily. That's if our system is controllable. Now, suppose this was a car, this system. We had a model of a vehicle. And now we wanted to drive it somewhere. Maybe this is the lateral dynamics of a vehicle. Could we? Could we go anywhere? How would we tell it to go to the right or go to the left? Do we have a command input anywhere? Do we have a reference input now, the way we've configured this? We're using our control all up by just weighting the state vector and feeding that into our control or input of our system. There's no way to say go 10 degrees right or go 10 degrees left. There's no reference input. We can't control this. If somebody kicked the car, it would shake, and it would shake just the way we designed it. So it responds very well to initial conditions. Its dynamics are governed by K, the way we picked it. So now if we kicked the car, it would move exactly how we told it to move. but we can't command it to go anywhere. That's one of the issues that we have to figure out or to address. So let me write that down. What we see here is that there's no way to provide a command signal to the system. What we have right here, right now, pictured is a regulatory system or a regulator design. It just regulates initial conditions. If you maybe move it away, if this was now a mass spring damper system, if you kick that mass, it would shake and get right back to where you wanted, or it would go to zero with the appropriate dynamics. But you couldn't tell it move to 2 centimeters or go to 4 centimeters. It wouldn't, you don't have that ability. There's no external or command signal right now in this block diagram. So this is a regulator system. We do have, though, the desired dynamics that we want. System has desired dynamic response to initial conditions. Can we introduce a command signal or a reference input? What do you think? Get out your coin. No, don't even get a coin out. I wouldn't ask this question if I didn't have the correct answer or a reasonable answer. Yes, we can introduce a reference input or a command signal. We just created u to be minus kx. Why don't we add a little bit more to that? So now let's talk about doing that. Let's now look at a reference input with state feedback. And for now, maybe it's best to just confine our discussion to a scalar input. Let's just assume a scalar input. Only one. Here's what we're going to do. Let's now let u of n be minus kx of n, but let's also include a reference signal, scaled by, let's say, some value n. If we have one reference signal and u is scalar, what's the dimension on capital N sub 1? Little u of n is 1 by 1. It's not m by 1. It's 1 by 1. It has one row, one column. It's a scalar. R, our reference, we just have one scalar reference. It's 1 by 1. We need this. And what is k? Let's say our system is fourth order. What's the dimension of capital K? So it's 1 by 4, but it's 1 row, 4 columns. We go rows, columns. So K is a 1 by 4 matrix. It needs to be 1 high to be compatible with U, because U is 1 high, isn't it? We need K times X. X is 4 by 1. So if you were just doing this, and again, draw a picture, you would say, well, X looks like this, R looks like this, U looks like this, and I need this to be compatible. I need the left side to be a scalar and the right side to end up with a scalar after I do the multiplication. And I have a plus sign. So these two terms have to be scalars when I finish with the selection of capital N sub 1 and capital K. I didn't write this very well, but K now, do you see it has to be 1 by 4? So that product of vectors, row vector and column vector, gives me a scalar. And N1 is 1 by 1, isn't it? N1 is just a scalar. Is that clear in that example? Questions on that? So this is now what I want with a full state feedback with an external reference signal. What do I have? Let me just sort of go through this rather quickly. We have our system dynamics. That hasn't changed. That's still x of n plus 1 is equal to phi x of n plus gamma u of n. But now our input is minus k x of n plus n sub 1 r of n. If we apply that u to our dynamics, we end up with x of n plus 1 equaling phi x of n plus gamma times minus k x of n plus n sub 1 r of n. Let's collect our like terms or coefficients for the state vector x, which will be matrices, and we can just keep the r term by itself, meaning we now have phi times or minus gamma k times x of n plus gamma n sub 1 r of n, and that's x of n plus 1. So that we haven't changed our closed loop system matrix. If we were happy with our choice of the full state feedback gain matrix K, we can keep it. We have the same full state feedback gain matrix. What we have introduced is the ability to now command or control our system. And what's our output? Our output now, y of n, is still h x of n. And if I said, give me the transfer function between the reference signal r and the output y, can you do that? This is a review for the final. What's the transfer function from the input r of z to the output y of z? Do you remember how to do that? We z-transform that dynamic equation. Z-transforming little x of n plus 1. And remember, x is a tall vector, isn't it? X could have 10 components. X is a vector. U we've already collapsed, but we still have R, and R we said let's just let that be a scalar. If we Z transform that dynamic equation, we have Z times X of Z equaling phi sub C, capital X of Z, plus gamma N1 R of Z. Are we okay with that? Just Z transforming, and I'm replacing phi sub C with phi minus gamma K, or replacing phi minus gamma K with phi sub C. What happens when I Z transform the output equation? That's not even dynamic, is it? That's just an algebraic relationship. I have Y of Z is equal to H X of Z. If I now work with the dynamic equation, I have Zi minus phi sub C X of Z is equal to gamma N1 R of Z, or X of Z is equal to Zi minus phi sub C inverse gamma N1 R of Z. And now I have what I wanted. My Y of Z is H times X of Z, but X of Z is Zi minus phi sub C inverse gamma N1 R of Z, and I now have my closed loop transfer function between the reference input R and the output Y. This I could call my T sub C of Z. N1 was a scalar, but I could use that to make my DC gain of T sub C of Z equal 1. So that if I commanded it to move 4, my output's going to go to 4, and I've got the dynamics that I wanted based on what's living inside phi sub C, which is the full state feedback gain matrix. We'll pick up with a little bit more of that and maybe do integral control and full state estimation. I'll see you next week. But don't forget, your homework is due tomorrow night, and our final is a week from Friday, starting at 6.